The James Webb Space Telescope spotted a large object, the object changing its trajectory in an unnatural manner.
The plume of gas around it is mostly carbon dioxide, 95% by mass, based on the Webb telescope data.
Allowing nickel to outgas, while iron remained bound in the nucleus.
The James Webb Space Telescope just turned its billion-dollar infrared eyes toward a mysterious visitor racing through our solar system.
There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe.
And what it found has left astronomers absolutely stunned. The discovery that stopped scientists. August 6th, 2025. The James Webb Space Telescope's near-infrared spectrograph locked onto 3I Atlas and captured something unprecedented in the history of astronomy.
We've got some fresh images of 3I Atlas, a third-ever interstellar object observed from Earth.
The way the NIR spec instrument works is by splitting light into its component wavelengths, creating a spectral fingerprint that reveals exactly what molecules are present in the comet's Coma, that is the cloud of gas and dust surrounding its nucleus.
This comet's really cool because it does have that tail from the sun's radiation blasting it, but it also has a forward-facing tail.
Now, every molecule absorbs and emits light at specific wavelengths, like a chemical barcode. Water has its own signature. Carbon monoxide, too, has its own signature, and the same as carbon dioxide. But what JWST saw was shocking. The spectral lines for carbon dioxide were dominant. Line after line, everything was screaming CO₂. Meanwhile, the water signatures were just faint, almost struggling to be noticed. When the data was processed and the ratios calculated, the numbers came back crystal clear. For every 1 molecule of water vapor escaping this comet, there were 8 molecules of carbon dioxide, 8 to 1.
We cannot really pinpoint the nucleus size. It's partially due to the size of the object, but also it's partially due to the activity.
Let's put this in context. The average comet in our solar system shows a CO₂ abundance of about 4% relative to water. Some comets are a bit richer, maybe reaching 10 or 12%. That's considered high, but 50%? That's a complete inversion of everything we consider normal. Even 2I Borisov, the previous interstellar comet that visited us back in 2019 and became famous for its extreme carbon monoxide abundance, didn't come close to breaking the rules this much.
Observing this rare comet that had water vapor in it.
Borisov was weird because it had 35 to 155% carbon monoxide compared to water, far higher than solar system comets. But its carbon dioxide was still relatively modest. 3I Atlas is playing a different game entirely. The statistical significance is what really drove this home for researchers. When you compare 3I Atlas to the entire population of studied comets, it sits 4.5 sigma above the expected trend line. In statistics, anything beyond 3 sigma is considered highly significant. But 4.5 sigma? That just can't happen by random chance.
How amazing is it that we humans have a word for something that literally flies between stars and so far?
So why does this matter so much? Because comets are chemical messengers. They're frozen time capsules that preserve the conditions of the protoplanetary disk where they formed billions and billions of years ago, around a star we'll never see, in a region of the galaxy we may never visit. Every molecule in that coma is telling us a story about planetary formation and cosmic chemistry in a place utterly alien to our experience.
The comet is here, the sun sends the solar wind to the comet, the sail goes behind the comet.
And the story 3I Atlas is telling is one we've never heard before. But to understand why this 8-to-1 ratio is so deeply disturbing to planetary scientists, we need to understand what comets should look like.
This comet is at the reverse side.
But is it nature or something else? We're gonna find out soon.
The chemistry of normal comets. Comets are often called dirty snowballs, but that description doesn't do them justice. They're more like frozen archaeological sites, layered records of the conditions that existed when our solar system was just beginning to take shape 4.6 billion years ago. When a star forms, it's surrounded by a massive disk of gas and dust called a protoplanetary disk. This disk is where planets, asteroids, and comets eventually merge.
Just like every planet is different, it looks like every comet is different. It has its own history to tell.
But this disk isn't uniform. It has temperature gradients. Close to the young star, it's scorching hot. But further out, it gets progressively colder. This temperature gradient creates what astronomers call ice lines or snow lines, which are invisible boundaries in the disk where different volatile compounds freeze solid.
that comet that entered human history on many occasions, and we found a cold, dead world.
Cross one of these lines moving outward from the star, and suddenly a particular molecule can condense into ice and start accumulating. Now, the water ice line sits at roughly 170 Kelvin, which is about minus 103 Celsius. Inside this line, water stays in vapor form and can't accumulate. Outside this line, water freezes and becomes the dominant ice in the disk. This is why the inner rocky planets, Mercury, Venus, Earth, Mars, are relatively poor in water, while the outer solar system is absolutely soaked with the stuff. This nested structure of ice lines explains why water dominates in typical comets.
There are golf ball-sized chunks of dry ice that are following the comet around, up to 1 million miles away from the nucleus.
Most comets in our solar system formed in the so-called snowball zone, where water ice is abundant, but carbon-rich ices are still relatively scarce. Now, 2I Borisov broke this mold by showing extraordinary carbon monoxide richness. The leading explanation was that Borisov formed much further out in its home star's protoplanetary disk, beyond even the carbon monoxide ice line, in an ultra-cold region where CO ice could dominate. But 3I Atlas? It's doing something different. It's not even carbon monoxide rich like Borisov to begin with. Instead, it is rich in carbon dioxide, and to an extreme we've never witnessed. So when JWST found a comet 8 times richer in carbon dioxide than water, it meant 3I Atlas formed under conditions that are way beyond anything we've ever known about planetary system formation, in ways we could never have imagined in a million years. 3 theories for the impossible ratio. Well, scientists love a good mystery, and 3I Atlas has given them pretty much something to keep them awake at night. Right now, there are 3 leading theories trying to explain this impossible chemistry. Each one is just as fascinating as the other, and of course, has its problems too. The first theory suggests that 3I Atlas formed right at the carbon dioxide ice line boundary in an unusually cold protoplanetary disk.
Initial observations showed that the comet had a high carbon dioxide to water ratio.
Imagine a disk around a red dwarf star, a small, cool star far less luminous than our Sun. These stars are the most common in the galaxy, making up about 70% of all stars. Their protoplanetary disks would be much colder overall than the disk that formed our solar system.
And also offers new insights into chemistry of distant star systems and their protoplanetary disks.
In such a cold disk, the carbon dioxide ice line would be pushed inward, closer to the star. The region where CO₂ ice dominates would be more extensive. If 3I Atlas formed right in this sweet spot, it could have accumulated massive amounts of carbon dioxide ice while water remained relatively scarce.
Researchers explored water activity on the comet and provided the first clear evidence that it was shedding water.
Supporting this theory is evidence that 3I Atlas's parent star system might have been carbon-rich rather than oxygen-rich. In a carbon-rich environment, carbon-bearing molecules like carbon dioxide and carbon monoxide would naturally be more abundant in the disk material. But here's the problem. Even in the coldest disk models, getting an 8-to-1 ratio is extremely difficult. The thermodynamics just don't favor carbon dioxide dominating over water to this degree. Something more is needed. Now, the second theory takes a completely different approach. What if 3I Atlas started with a more normal composition, but spent billions of years being bombarded by radiation in interstellar space? Galactic cosmic rays absolutely are relentless. Over millions and billions of years, they can alter the surface chemistry of objects exposed to them. The idea here is that this radiation preferentially stripped away lighter volatile molecules like water, while leaving the heavier carbon dioxide molecules behind. This theory gains serious credibility when you consider 3I Atlas's age. Trajectory analysis suggests this comet is ancient, potentially 7 to 11 billion years old, formed when the Milky Way was young.
We actually live in the middle of this disk of gas and dust, and that obscures our view of the larger Milky Way.
That's 3 to 5 billion years older than our entire solar system. How insane is that? So if 3I Atlas has been drifting through interstellar space for 10 billion years, exposed to relentless cosmic radiation, its surface chemistry could have been dramatically altered. The radiation would act like a slow, persistent wind, eroding and modifying the ice over cosmic timescales. But even this theory has a weakness. Radiation processing typically creates a hard, dark crust on the surface. You'd expect this crust to seal in the pristine material underneath. Yet 3I Atlas is actively venting. A whole lot. Something has broken through that crust and is releasing that interior material. The third theory is perhaps the most intriguing because it suggests we're being fooled by what we're seeing right now. Carbon dioxide turns from ice to gas at much lower temperatures than water ice.
And since it has this very bizarre composition, with the highly enriched carbon dioxide Coma,
at 3 I-Atlas's current distance from the Sun, roughly 4 astronomical units, carbon dioxide is vaporizing vigorously, while water ice remains largely locked in solid form. The theory here suggests that beneath a surface layer rich in carbon dioxide ice, there could be massive reserves of water ice that simply haven't started sublimating yet.
The plume of gas around it is mostly carbon dioxide, 95% by mass.
As the comet gets closer to the Sun and heats up, this hidden water reservoir will begin to dominate, and the ratio will flip back to something more normal. This would mean the 8-to-1 ratio is simply temporary, a snapshot of a comet that's just beginning to wake up as it approaches solar warmth. The problem here is that JWST detected hydroxyl radicals, which are fragments of water molecules broken apart by solar ultraviolet light. This means water is already sublimating and being destroyed in the Coma. If there were massive water reserves close to the surface, we should be seeing more of it already. Still, this theory can't be completely ruled out until 3 I-Atlas gets much closer to the Sun and we see what happens. Each theory is compelling, each theory has holes, and the truth might be some combination of all three. But there's another detail about 3 I-Atlas that makes this story even stranger. The cosmic age. When you trace 3 I-Atlas's trajectory backward through time, something remarkable emerges. This isn't just an object from another star system.
This star system is not enriched in iron.
This is potentially a relic from the ancient galaxy. Looking at the velocity, the trajectory angle, and all the numbers that tell you where something came from and how long it's been traveling, there's a 68% confidence that 3 I-Atlas is between 7.6 and 14 billion years old. The median estimate sits at 10 billion years. 10 billion years. Our solar system is barely 4.6 billion years old. The Earth itself is 4.5 billion years old. When 3 I-Atlas formed, the universe itself was less than half its current age. 3 I-Atlas is a message in a bottle from that ancient era.
We've got some fresh images of 3 I-Atlas, the third ever interstellar object.
For 10 billion years, it's been coasting through the galaxy at 61 kilometers per second, frozen solid, preserving the chemistry of its birth environment. It may have witnessed dozens of galactic rotations, passed through spiral arms and stellar nurseries, threaded its way through interstellar clouds, and emerged harmed, until now. Until it happened to pass within a few astronomical units of our Sun and began to wake up. The fact that this ancient object shows such extreme carbon dioxide richness suggests that whatever star system created, it had a chemistry wildly different from our own.
The plume of gas around it is mostly carbon dioxide, 95% by mass, based on the Webb Telescope data.
Or perhaps 3 I-Atlas is showing us what normal actually looks like across the galaxy, and our solar system's water-rich chemistry is the exception, not the rule. But the carbon dioxide dominance isn't the only chemical surprise JWST discovered. What you are about to see next is something even more complex. The complete chemical portrait. The full spectroscopic analysis from JWST and ground-based telescopes has revealed a chemical inventory that's both familiar and deeply alien.
I was disappointed. I would have been much more excited if we have found evidence for an alien civilization.
Yes, carbon dioxide dominates at roughly 50 to 53% relative to water, but carbon monoxide is also present, detected at about 9%. This makes 3 I-Atlas a hybrid, both CO₂ rich like no comet we've seen, and moderately CO rich like Borisov, but to a lesser degree. Water vapor is there, confirming this is indeed a comet, not some bizarre rocky asteroid, but at only 4 to 6%, water is a supporting player rather than the star of the show. Then there's carbonyl sulfide, OCS, a sulfur-bearing molecule that's been detected in very tiny amounts. This is significant because sulfur chemistry is a sensitive tracer of formation conditions. The presence of OCS suggests sulfur was available in the protoplanetary disk and incorporated into ices alongside carbon and oxygen. Water ice grains have been detected in the Coma as well, not just vapor. These grains are being ejected along with the gas, creating that dust tail that makes the comet visible to telescopes. The dust-to-gas ratio has been measured at roughly 1.4, which is reasonably typical for active comets.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
There's evidence of sunward enhancement in the outgassing pattern, meaning the side of the comet facing the sun is more active than the night side. This is expected and indicates the sublimation is being driven by solar heating, not by some internal heat source. Interestingly, Observations from ground-based telescopes detected emissions consistent with diatomic carbon CO₂ and possibly cyanide CN. These are elements created when larger organic molecules are broken apart by sunlight. Their presence hints at complex carbon chemistry locked in the nucleus. All of this chemical weirdness paints a picture of an object that's both interestingly familiar, because it's a comet after all, with ice and dust and sublimation, and profoundly alien in its specific chemistry. And this raises an unsettling question that goes way beyond just one weird comet: what this means for planetary system diversity. The discovery of 3I Atlas forces us to confront an uncomfortable possibility. Our solar system might be the exception, not the rule. For decades, we've built our understanding of planetary formation on one primary data set: our own solar system. Every model, every assumption, every prediction has been calibrated to match what we see around our sun. Water-rich comets, rocky inner planets, gas giants in the middle, ice giants further out. This is our template. But what if this template is just one possibility among thousands? The chemistry of 3I Atlas suggests that planetary systems around red dwarf stars, which remember are 70% of all stars, might routinely form with carbon dioxide-rich environments. If protoplanetary disks around these cool stars are CO₂-dominated rather than water-dominated, then the planets forming in those systems would have completely different volatile inventories. Imagine a terrestrial planet forming in such a system. Instead of oceans of water, you might have massive carbon dioxide ice caps, or a thick CO₂ atmosphere far more extreme than Venus. The surface chemistry would be dominated by carbonates and carbon-based minerals rather than silicates and water-weathered rocks. Could life arise in such an environment? On Earth, life is fundamentally tied to liquid water, but some organisms have been discovered thriving in incredibly hostile conditions.
It is only the third time we have detected an object that has come from beyond our solar system.
If liquid carbon dioxide can exist under certain pressure and temperature conditions, could it serve as a solvent for exotic biochemistry? These aren't just idle speculations anymore. Every exoplanet atmosphere we study with JWST is showing unexpected diversity. We've found planets with silicon-bearing clouds and carbon-to-oxygen ratios that flip conventional wisdom. The universe is chemically diverse in ways we're only beginning to understand. But here's the statistical problem that keeps astronomers up at night. Objects like 3I Atlas should be extraordinarily rare if they're as massive as their brightness suggests.
This object has just been discovered. 3I Atlas was discovered on July 1st by the NASA-funded Atlas survey.
Based on the amount of light 3I Atlas reflects, the nucleus must be really huge, estimated to be roughly 33 billion tons minimum. For a rocky or icy object this large to be wandering through interstellar space is statistically improbable. Avi Loeb, who's been vocal about the unusual aspects of interstellar visitors, has calculated that the limited reservoir of large rocky objects drifting between stars could only deliver something this massive to our solar system, perhaps once every 10,000 years or longer. Yet here we are, only a few years after Oumuamua and 2I Borisov, with a third interstellar visitor that's potentially even larger and stranger. Either we're extraordinarily lucky to witness a cosmic coincidence, or interstellar objects are far more common than our models predict, and the galaxy is teeming with these wandering fragments of broken planetary systems. As 3I Atlas races toward its closest approach to the Sun, we're in a race against time to extract every piece of information we can before it vanishes. The observation window closing.
3I Atlas is hiding behind the Sun, and whatever it does during this time will remain a mystery for us.
Right now, 3I Atlas is approximately 4 astronomical units from the Sun, roughly the distance of Jupiter's orbit. Every day it's plunging closer to its closest approach, which will occur on October 29, 2025. But there's a cruel twist of celestial geometry. When 3I Atlas reaches perihelion, it will be on the opposite side of the Sun from Earth. Solar glare will make observations virtually impossible from our planet. The most active phase of this comet's journey through our solar system will be completely hidden from our view.
Now, the interstellar visitor named 3I Atlas it came beyond our solar system.
Before that happens, there's a critical observation opportunity on October 3rd, when 3I Atlas passes within 29 million kilometers of Mars. That's roughly 75 times the distance between Earth and our moon. Astronomers are scrambling to coordinate observations using Mars orbiters. The ESA's Trace Gas Orbiter and NASA's MAVEN spacecraft both carry imaging equipment that could potentially capture close-up views of 3I Atlas as it whips past the red planet. These observations could reveal surface features and provide direct measurements of the nucleus size and shape. After this perihelion, 3I Atlas will begin moving away from the Sun by mid-December 2025. It will pass within 1.8 astronomical units of Earth, about 170 million kilometers. Not particularly close by asteroid standards, but close enough for powerful telescopes to study it in detail. After December, the comet will continue on its hyperbolic trajectory, passing Jupiter's orbit in March 2026 at a distance of 33 million kilometers from the giant planet.
Since this isn't due to geometry, researchers are examining whether the composition or grain size of the ejected material.
Jupiter's immense gravity will give 3I Atlas a final gravitational boost, accelerating it on its way out of the solar system. And then, it will be gone. Back into the interstellar void. In a few thousand years, it will be far beyond the Kuiper Belt, beyond the heliopause. Once again, just another frozen chunk of ancient ice coasting through the galaxy. JWST has already secured additional observation time for 3I Atlas in the coming months. The plan is to monitor changes in the spectral signatures as solar heating intensifies. Will carbon dioxide continue to dominate? Will water start to surge? Will we detect new molecules like methane, ammonia, and ethane that remain frozen at the current distance? Ground-based observatories are also tracking it continuously. The European Southern Observatory's Very Large Telescope, the Gemini Observatory, and the Keck telescopes in Hawaii are all gathering data. Every spectrum, every image, every data point is precious. The urgency is real. This is a once-in-a-lifetime event. We're living in the brief window when 3I Atlas is close enough and warm enough to study. But what we've already learned is rewriting the textbooks. The bigger picture. Let's zoom out for a moment and consider what we're really witnessing. In all of human history, we've confirmed exactly 3 interstellar objects passing through our solar system, and they couldn't be more different from each other. Oumuamua, discovered in 2017, showed no cometary activity whatsoever. No coma, no tail, just a tumbling, elongated object moving at high speed. Its composition remains a mystery. Was it a nitrogen iceberg from a Pluto-like world, as some research suggests? Was it a hydrogen iceberg, as other papers propose? Was it something else entirely? We still don't know. 2I Borisov, discovered in 2019, was more conventional, an active comet with a clear coma and tail, but its chemistry was extreme, with carbon monoxide abundances far exceeding anything in our solar system. It told us that comets from other stars could be dramatically different in composition.
This could give us our best close-up look at an interstellar object's surface, and potentially resolve the question of whether we're seeing reflected sunlight.
Now 3I Atlas has arrived, and it's broken different rules. Not carbon monoxide dominant like Borisov, but carbon dioxide dominant in a way we've never seen. Ancient, probably 10 billion years old, carrying chemistry from the galaxy's youth. 3 objects, 3 completely different chemical signatures, 3 different stories. What does this tell us? That interstellar space is filled with diversity. Planetary systems produce an astonishing range of outcomes. The cosmos refuses to conform to our expectations, and we're about to get much better at finding these visitors. The Vera C. Rubin Observatory, which achieved first light in 2025, is an absolute game changer. This facility in Chile uses a massive 8.4-meter mirror and a 3.2 gigapixel camera to scan the entire visible sky every few nights.
Equipped with the world's largest digital camera and an 8.4-meter telescope, it captured millions of galaxies.
Its sensitivity and coverage mean it will detect dozens of interstellar objects annually. Within a few years, we'll go from having studied 3 interstellar visitors to having studied dozens, maybe hundreds. We'll start to see patterns. We'll build statistical distributions of compositions, trajectories, and sizes. We'll begin to understand which chemistries are common and which are truly anomalous. And in 2029, ESA's Comet Interceptor mission will launch, a spacecraft specifically designed to explore with a new interstellar visitor on its first passage through the inner solar system. When the next object arrives, we won't just observe it from Earth. We'll send a probe to meet it, fly through its coma, sample its composition directly, and image its nucleus up close. This is the beginning of a new era in archaeology.
Allowing nickel to outgas, while iron remained bound in the nucleus.
3I Atlas's extreme carbon dioxide ratio is just the first chapter in this story. It's teaching us that the chemical space for comet compositions is far broader than we imagined. But that 8-to-1 ratio is also raising more questions than it answers, and that's exactly what great discoveries do. So here we are, staring at spectral data that defies decades of assumptions.
NASA Infrared Telescope Facility have revealed strong water ice signatures mixed with carbonaceous minerals and silicate.
The questions lie unanswered before us. Is 3I Atlas a product of ice line birth in an ultra-cold disk around a red dwarf? Is it a radiation-processed relic that's been chemically altered for 10 billion years? Or are we simply seeing the early stages of sublimation, and the water is waiting beneath the surface to surge forth as the comet approaches the sun? Right now, all three explanations remain on the table. The data support each theory in different ways. The data contradict each theory in different ways. What makes this discovery historically significant isn't just the weird ratio itself, it's what that ratio represents. This is a chemical fingerprint from 7 to 11 billion years ago, from a stellar environment so different from our own that we can barely model it. Our window to study this messenger is closing rapidly. By late October, it disappears behind the sun. By December, it's already heading back toward the interstellar void. By March, Jupiter flings it outward, and it's gone forever. But what we learn in these few precious months could reshape our understanding of planetary system diversity across the galaxy. Every spectrum JWST captures is irreplaceable. Every observation is a gift. And right now, as 3I Atlas streams through our solar system exhaling its alien breath of carbon dioxide, and that's just the opening line of a conversation that will last generations. Thanks for watching. See you in the next one.